this computer. Okay, so welcome to the CE-529 lab. And what we're going to do now is go over a couple of items. We're going to just look over our Canvas website first. And then in our Canvas portal, I'm going to introduce, and then we'll go over the lecture for Introduction to Simulation. And then I'll go over sort of two assignments that I'll have you do over the coming week. They're both going to be due one before the lecture on Tuesday, and then one before the lab on Tuesday. So they're both going to be due Tuesday. So I'm going to go over those assignments. So let me go ahead and share my screen. So you should be able to see my screen here. And let's see. So I should probably switch to student view. So this is your syllabus. So if you click here, that takes you to your syllabus. So this takes you to the syllabus, and then perhaps I can. Okay, so this takes you to the syllabus, as I said. So, right, and then there's a class meeting Zoom link. This is where you can find the Zoom link for the class and the lab, by the way. So they both share the link. So, and then I have made this playlist available to you on YouTube. So basically whatever syllabus discussion we had today. So what I'll try to do is I'll have sort of like what major topic we discussed and then the date of the lecture. And then if there is things that I want you to consider, then I'll probably put that in the description if you want to specifically look at what topic we discussed during that lecture. So that sort of is going to be the plan going forward. If I get delayed, just remind me that I still need to post that lecture, and I will. But my goal will be to sort of post these lecture videos as soon as possible. So in case you missed out, sometimes these lectures are good for even just refreshing the material too, right? Like sometimes when you work on the homework, you might not remember what we talked about. So hopefully this video recording would come in handy. So I'll try to make this available. So I already made the syllabus discussion available. Hopefully this was not something that you need to go back to, but if you do, it's all there. And then this is the office hour Zoom link. So this is the Zoom link that you'll use to connect with me during the office hours. And that Zoom link is different from your lecture Zoom link. So if you click on this, you'll find a different Zoom link in the new window. So it kind of takes you to a different meeting. So just remember that. And then, so we'll talk about these labs, but first, so I'll have sort of a different panel for the lab. So I'm not going to utilize that 529.02 section for the lab, but I'll just have sort of one module for that we use for the labs. This is sort of the lab 0 that we're going to work on today. But in a little bit, before we do that, I'll have the introduction to simulation assignment first. Okay? I mean the lecture first. Okay, so I'm just going to go into slideshow mode. Okay, very well. So we're going to get started with the sort of the rationale for using graphic simulation or any kind of simulation and modeling. Why do we do modeling in the transportation field? Okay, so that's sort of what and why, and then we'll learn about different sort of big picture aspects of simulation, and then after we've done that, we'll go over some examples, and then using those examples, we'll sort of start to learn about what all is actually needed to do all of this work, right? So before I used to do that, first thing I do in the class is want to show you a video. So go back to the simulation class. So if I click on the homework number 1, oh, it's locked. Well, it's locked. Okay, so I need to leave student view. So I want to show you this video first. Huh. Okay. not a very auspicious start here. I'm going to go ahead and pause this. And let me pause this. Okay, so let's see. Okay, so now we have the simulation up on the screen. So you probably recognize this location, right? What is that? What is that location? It's the campus. It's the Cal Poly campus, right? So you can see that. So I'm gonna show you what kind of things are possible with microscopic simulation. So this is a video recording of a model that one of my students did a while ago of the traffic moving through campus. And it's an old model. Now we're zooming into different locations. Probably can recognize these locations. Even though you don't see the stop sign, you can see that the vehicles do behave as if there is a stop sign. But you're able to sort of, and this is speed up, of course, right? So this is speed up version of the model. So you can see sort of different interaction between the very different vehicles. And this is near the stadium, the crosswalk. And when the pedestrian comes, yes, it does. And that's what it's showing right now because it's the Cal Poly AM traffic simulation. It's the morning level. So the comment was the traffic sort of sucks in the morning, which is correct. But I think maybe it has gotten a little bit better because maybe not everybody's coming in at 8 o'clock. And then you could see, I don't know if you guys saw that. I was talking about something else, but you could see how it sort of captures the behavior. Okay, I'm gonna. So keep an eye on that green truck that comes by. Right, so these kind of things do happen, right? So we do account for that in our model. And there might be some folks like, who have a certain route to get to, but they get stuck in the wrong lane. And then they have to make a change last minute. So that's all based on what the destination was assigned to that truck. And then it realized that, hey, I'm not in the right lane. So it has to move out. So we did model the stop sign. It's not shown here as a picture, but the stop sign is in fact modeled there. So this is now back near Performing Arts Center. And this model is a little bit older now. So it might not be capturing the exact trends as they exist now because now we have sort of maybe more faculty, more students. There comes the bus as merges in and out. So this is the crosswalk. We don't have that traffic signal that's there now because this is an older model. And now this is back near the library. Okay, so I think then we zoom back out, and that's okay. So we don't have much left. So anyway, so this is an example of the kinds of model you can build using the traffic simulation software that we have. Right. So this is the kind of thing that you are able to do using the simulation model. So I'm going to go ahead and share my Chrome screen back again, and then I'm going to close this tab. And then you can find these types of examples all over YouTube, by the way. So you could go back and look at all sorts of things. So what I want to do is just wanted to show that to you before we start to describe what and why of simulation. But this is the kind of model that you can develop. with your traffic simulation. So the packages that we now have. So I'm going to go ahead and slideshow. So what is simulation? Simulation is the imitation of the operation of a real world system over time. What's a system then? A system is a collection of entities that interact to accomplish a certain goal, certain logical end. So when we talk about the transportation system simulation, we're trying to move people and goods from their origins to their destinations. And then we're trying to model that system in a simulation environment. It involves generation of artificial runs of the system and the drawing of the inferences based on that. So when I showed you that Cal Poly morning traffic simulation model, that model was essentially trying to show you how the system performs. And we're not as modelers of the system, we are not actually as interested in that simulation that I just showed you. Sometimes it could be useful for demonstration purposes, but what we are interested more in is the underlying data that comes out. So this model that I showed you was developed to figure out how much vehicular emissions are generated at Cal Poly campus due to the movement of vehicles. Right? So you can generate performance measures such as total emissions. You can create how much delay is going to happen at certain lengths of that road. So when you say that traffic sort of sucks when you're coming into the morning, yeah, sucks is one way to put it, but then we want to be able to quantify what does suck mean really, right? How much does it suck, right? So we want to be able to say, so yeah, if you're get stuck at like, you get out of your, if you're coming from North County, for example, on US 101, you take the exit and then you merge onto was that California Boulevard, right? It's California, we merge onto California Boulevard. From that point to the building 13 parking lot, it takes you 4 minutes to get there. But if this conditions was free flow, probably only takes like maybe 50 seconds. So now you can quantify what happens when the traffic is backed up on these signals and all these. So now you can figure out how much does it back up. Now the value of simulation is not necessarily in showing these conditions, because you can actually measure that time, that 4-minute travel time, but just by driving around, right? You could bike, or you could be a pedestrian. You can observe that system that way. But the value of simulation really comes in when you want to do something. So once you model the base condition and all the demands and everything, now let's say somebody says, hey, why don't we put a roundabout in the middle? If we could, right? I don't think that location really lends itself to a roundabout because of the whole railway track and the limited right of way and all that. But you could figure out, okay, let's see if you want to make certain improvements to that system. How would the system behave now? Right? You could see, you can model if we could direct 5, 10, 15% of the trips from cars to bicycles, or from cars to the bus. What would happen to how much improvement could we make? Right? Things like that. So now the value of simulation is being able to generate the artificial runs for the existing scenarios, and then perhaps implement some changes, not in the real world first, do it in the simulation, and then quantify what would happen, right? So it's a very sort of typical practice to demonstrate what would happen if you convert a signalized intersection into a roundabout, right? It's a very, very typical project that a consultant company might undertake, is that build the model for the existing condition, now build a roundabout into that model, and then do the analysis before and after, right? So look at those conditions, things like that. So, but what you're doing is you're creating a replica of the system and then running the runs through it. And then obviously there is stochasticity and all that will come to. So how do you analyze a system, right? So there are simulation is obviously not the only way to analyze the system. You can analyze the system by actually experimenting with the actual system. So you could, maybe do some pilot cases, right? And sometimes you do that, but those pilot tests could be very expensive, right? So we could do a pilot test, and sometimes the world gives us sort of these natural experiments, right? When everybody was working virtually, obviously there was no traffic here, right? You could come and go as you please. So there could be some experiments or some events that could happen with the real system. But a lot of time that doesn't work. You can't just put a roundabout, or you might want to test like 3 different categories of roundabout, what works best. You might have multiple solutions beyond roundabout, whatever it is. So you could have different solutions that you want to test, and you can't probably implement all of those into a system. You cannot implement all of those things into the real world. And so you can't test all of them. So that's where sort of working with a model of the system could be useful. Sometimes those models could be sort of physical models, right? So you could build like, so physical models are what architects deal with quite a bit, right? So they're always kind of thinking about physical models of the system. What we are going to do in this class are going to be, you can classify them. I would classify them as more like mathematical models. So they're basically looking at the behavioral aspects of interaction between the users, and then they're demonstrating that in the form of a simulation model, right? So basically what we're doing is we are building a mathematical model. So PTV vSim, what it does is builds a mathematical model of how users are going to interact, how close they're going to get, and how much sort of time they will take to go from point A to point B. So they generate all those things, but they can also generate sort of a replica of the physical system. So the video that you just saw, I think it's a physical representation of the mathematical model that they built. Does that make sense? Right? So the model underlying model is mathematical, right? The interactions are all basically based on the behavioral model, the model parameters that you're going to see in vSim later on. But then they're shown in the form of a physical model. Like, you can see the vehicles moving, right? So, but the model itself is not a physical model. The underlying model is in fact mathematical. And then you can analyze mathematical models using sort of analytical approaches, analytical solutions, and or you can do simulation. So now analytical solutions would be something like what you learn in CE-529 traffic engineering course, when we are, let's say, we are trying to do the analysis based on a highway capacity map, HCM, right? So like they have Webster model for delay or whatever, like intersection delay. So there you're not actually measuring the delay, you're estimating the delay using some kind of an analytical approach. And sometimes they work just fine, but then sometimes simulation approach is better because there might be elements of the system for which you might not have an analytical solution, right? So that sort of is the decision tree of how you can potentially analyze the system. So if you ask me, what we are doing in this class is essentially sort of following this train, right? So this is what we are following here. So we are so what we're doing is following this train here, and then doing the simulation models. Okay, so we're following this sort of path here. So some modeling concepts that would be useful to think about. The system, that's the real thing, the transportation system. Model is a representation of the system. And then an event is an occurrence which changes the state of the system. So that event could be a lane closure. So sometimes we are really interested in sort of these short-term events, like lane closures due to a crash, or it could be like a fixed signal failure, right? Or it could be, you just let out, maybe due to emergency or whatever, you have to evacuate a whole campus, right? It could be any event. So event is part of the system. So any occurrence, it changes the system. And then, so that's what we are analyzing here. And then one more modeling concept is dynamic versus static models, discrete versus continuous event models, and deterministic versus the stochastic model. So we'll probably get to each of these in the next slides. So let's talk about the static versus dynamic system first. So an easy way to think about this is, does time play a role in modeling of the system? Static models represent a system at a given point in time, or represent a system where time doesn't play any role. Okay, so this is what your lab 0 is going to be about. I'm going to give you an example of sort of a static simulation that you're going to do to estimate the value for pi, using pi is basically the ratio between the diameter and the circumference of a circle. So that's what pi is, but how can you estimate pi using a simulation-based approach? So we're going to learn to do that, and that would be an example of static simulation. It has nothing to do with time at all. The system does not change by time. But when you're modeling transportation system, they require sort of dynamic models. Okay, so our models that we build, even if we are, and this is not to be confused necessarily with the static assignments, right? Static assignments or dynamic traffic assignment. Then you're talking about like whether time plays a role in the assignment of traffic, right? But all our models essentially are going to be dynamic in nature, because the state of the system does change over time. So transportation systems, when we're modeling them, they do require dynamic models, because the state of the system does change over time. Right. So, and then we can look at continuous versus discrete. So this is the second sort of modeling concept that I want to make sure that we understand: static versus, continuous versus discrete. Do the model state variables change continuously with respect to time? Right. So is the change that's going to happen, is it continuous change, or is it changing like, discretely, like one event by one event by one event? Now, the decision to use a discrete or continuous model for a given system depends on the objective of the study, right? So for example, think about this. And this is a little bit of a harder concept to grasp sometimes. But think about this. If you're modeling a queue, that queue could be at a toll plaza, that queue could be at a bank teller, for all I care, right? It could be anywhere. And then that toll plaza is being served, that vehicle queue is being served by an attendant. The system entities will be your vehicle queue and the attendant, right? So, and then the system events will be vehicle arrival and vehicle departure. So with that kind of system, would you characterize that as a discrete system or a continuous system? So the third bullet point, in this example, would you call it a discrete system or a continuous system? Yes, please.
Like, would it be continuous because there's always going to be an accident and all the cars go to the same spot?
So the response is that maybe it's a continuous system because all the cars are going to pass through the same spot as they come and go. I think when we model it, I think a better way to model that, I mean, we could think about it in those terms. But I think when you're modeling it, these things would be sort of, they're better off modeled as sort of discrete events. Because what you want to do is, you want to be able to model sort of their serving time, right? So because ultimately you're interested in when does the queue dissipate, how much time does it take to serve each customer, and all of that. So I think servicing of each customer sort of becomes your discrete event. So you're sometimes better off modeling this type of phenomenon as a discrete event. Now, actually, this is very interesting to know because, and it's an important discussion item, because the way you responded, I think that's a very common response, and that could lead to some sort of understandings about how Wilson works also, by the way. So the model that you saw, that I showed you, Actually, it's a discrete model. It's not like the Cal Poly campus traffic simulation, even though you're seeing each vehicle movement. Those are actually discrete models because what they're modeling is every 10th of a second, and then you can describe the sort of the granularity of that system or that model. But what happens is that vSim is actually modeling the movement of each vehicle every 10th of a second or every 100th of a second. So actually it's being modeled as a discrete system. Okay, so when we do vSim modeling, it's a discrete model. Even though obviously we think of sort of these things as flow and all that. Now, how do you differentiate between, do we ever use a continuous modeling? Actually, we do. When do we use continuous modeling? So think about what you need to think about is, let's say, remember how we were used to model the traffic flow versus density? And it's the curve that I showed you this morning as well in the lecture. That's a continuous flow modeling. You're treating the whole of traffic as one flow, and then you're able to modeling speed versus, you're able to model speed versus density and the density versus flow. Those will be your continuous model. So a model of traffic flow would be discrete if the characteristics and movement of individual cars are important. So that's what is important for us in vSim model, right? We're doing micro level modeling, and those are discrete models. But when you're talking about traffic flow as sort of a continuous flow, stream of flow, then you get into what we call a continuous model. And now that continuous model will be the speed flow models and all of that. And one thing that we're going to do in this class in week 4 is we're going to talk about how sort of these discrete assumptions about how vehicles interact with each other or road users interact with each other actually leads to the continuous model, because they're all ultimately they're all representations of the same system, right? I mean, if you're modeling the traffic flow on a freeway and you're doing it vehicle by vehicle, you're doing a discrete model of that, right? And it's the same flow. You can model it in a continuous fashion too by looking at when you do your shock wave analysis, for example, that we're also going to do. So then you're treating that as a continuous flow. And those two things, in fact, point to the same thing. How those two things are consistent with each other, we're going to learn that. But those are two different modeling approaches. One is discrete, where you're looking at individual vehicles every 10th of a second or whatever granularity you want to use. And the other one is basically treating that as sort of a flow of fluid, right? So that's basically the difference between continuous and discrete. But remember, the vSim models that we develop, they're all going to be discrete models, okay? Because we are focusing on individual vehicles at every 10th of a second or 100th of a second or whatever you want to specify, you could. And what you learned in 321, when you were doing Green Shields model, if that rings a bell, or sort of Q equal to flow equal to speed times density, those things, those were your continuous. Okay, first of all, any questions about this? And feel free to hop on Zoom and then type your questions if that's something that's you feel it's easier. Yes, please.
So is there a difference between like microscopic versus macroscopic simulations, where usually microscopic would be the discrete ones? And then...
Yeah, so when you're doing macro level project, macro level would mean that you're basically looking at a bigger area, and then as your area size grows bigger, you become more interested in, like, you cannot, it's very hard to model the individual user interaction at that level. Like at that scale, I'm sorry, at that scale, it's hard to model what's happening between an individual. And then that way, and so when you're doing macro level modeling, yeah, so then that's when you sort of get into this continuous flow model, as you're saying. But as you sort of go towards micro level, that's when you're doing the discrete modeling. So that makes perfect sense. Mm-hmm. And then this is the question of deterministic versus stochastic, right? So does the model contain any probabilistic components, right? So this is a question to think about here would be, consider a toll booth. where the mean headway, the average headway for arriving cars is 15 seconds. So on average, the cars arrive every 15 seconds. One car arrives every 15 seconds. So in a minute, you can expect 4 cars. So if you sort of observe it over long term, like, so if you observe that toll plaza for 1 hour or 2 hours, you will see 360 cars per hour. Right? So did I do that right? So 4 cars, no, 240 cars per hour. 240 cars, right? Because one car is arriving every 15 seconds on average. In a minute, you would expect 4 cars, and in an hour, you would expect 240 cars. Right? It's a toll booth, right? And the mean toll collection time, and basically the attendant takes 12 seconds to take the change on average, take the change, and whatever like they need to do, or give the receipt, whatever, it takes 12 seconds. So my question to you is, do the cars ever get delayed at that toll plaza? Yes. So let me, so the response is, there is the startup time and stopping time and all that. And let me say that, let's say these 15 seconds and 12 seconds account for those startups and the startup time and the stopping time. So that's basically all accounted for. So every car basically takes 15 seconds, including their startup and response time. And then 12 seconds is what the attendant takes, accounting for all those things. Yes.
And so you still may have a delay because even if like 15 seconds is the average, like there may be sometimes when it's a shorter.
Yeah, this is a very good point. This is exactly what I was trying to get at is, so even though the average says 15 seconds, you could have certain times where cars, the gap between 2 consecutive cars might be 10 seconds. Some other time of the day it could be 30 seconds or whatever, right? So these are averages. Now, whether you have a deterministic system, if you have a completely deterministic system, then you will say, yes, a car arrives every 15 seconds and that's it. But we typically don't have that. In reality, most of our systems are stochastic in nature. So that's why there is going to be delay, because not even if you account for all that startup and lost time and everything, there might be delays because these 15 seconds is an average, and it's not always going to be 15 seconds. There might be some smaller delays, some larger delays. Now, so you can analyze this analytically as well. Like, so sometimes there are ways to handling this. And I think we do that in signalized intersections. Sometimes we model them as sort of a deterministic system and then add a penalty to the delay. We'll just add a penalty term to the delay to increase that delay to account for this type of things that might happen, right? So that's one way of doing that. Or you could, instead of say, I mean, in VSIM, for example, if you have 240 cars per hour, 240 vehicles per hour originating from a point, you let VSIM know that in every run, you pull a distribution, you pull that number of how many cars are actually going to leave from a distribution that has an average of 240 and a certain variance within that. So basically a normal distribution around the average of 240. And then sometimes VSIM will, depending upon the seed number that you're using, sometimes VSIM will have 250 cars come out of that. Sometimes it will have only 230 or whatever, some number in between. So that you are, and this makes sense because our traffic flows work like that. We don't exactly get the same thing every day. And that's why a good practice when you're doing the simulation is, that you always run the model at multiple seed numbers, and then you average the performance measures for multiple seed numbers. So you'll run the same model maybe 5 times or 10 times, and then you average those runs up. And then how many times you do it depends on a lot of factors that we'll get into later on. But why do we use multiple seed numbers when we are running simulation models? Is because of this, because we're trying to account for that stochasticity. Okay. So The questions that you need to ask is, what type of input data would you need to build your model? How close is your model to reality? How long are you running the model for? How many number of runs you should do? And then output analysis. What type of output analysis do you need? What is the purpose of doing all of these? So kind of thinking about what performance measures you might have in the model. Right? So these are some of the things that we worry about. So we'll come back to these. So these questions are kind of important because we'll come back to at least the first one for our homework problem. Okay, so I'll come back to this in a little bit. So what are some of the advantages of using traffic simulation? It's a good decision aid. You know, it can help you make decisions. It has time stretching and contraction capability. So you can sort of run the model rather quickly by having a longer length simulated in a short amount of time. You can figure out cause and effect type relationships. So you could have sort of a signalized intersection replaced with a roundabout, and you can say the reduction in delay is caused by that roundabout. You can explore multiple possibilities that you could not do if you always had to tinker with the real world. You can diagnose problems. You can look up where your cues are happening, right? You can, if you change the system, you can figure out where the cues are going to go now, where the problem points might be. You can look those up. Identification of constraints or bottlenecks or whatever, right? So the different locations where there might be bottleneck, you could do that. And then this last one is what I showed you in that video, is the visualization of trends. You can visualize those trends at different locations. You could see how the vehicle movement is going to be. And a lot of times, you know, agencies were, when they're first proposing roundabouts or any kind of novel solution to the transportation system, they use these 3D animations to demonstrate to people how the system is going to behave. And then you could, that's why you could use sometimes you can build consensus with that. You can prepare people for change. It's a cost-effective investment. When you're trying to make changes to the real world system, it could be a very costly endeavor, right? So you wanna, it could help you make decisions in a cost-effective way. And then simulation can also be used for training aid capability, and we're not actually going to go into that a whole lot in this class, but there is a whole class of simulation models that are used for training the users, right? And those training models, those are sometimes called driving simulator. So you could have sort of like, you know, where with a steering wheel, an accelerator and all that built into in a static sort of place. And then you could train the drivers using that, right? And then you could have VR headsets now where you can train pedestrians on how to sort of cross that model. So all of that is also an example of simulation. So simulation can be used as training aid, but that's not the focus of this class. So we're not actually going to get into that too much here in this class, or at all really. But remember, all of those things are also simulation, where you simulate the real world environment and put the user in it. And then based on their behavior in that simulated environment, you can make assumptions, or you can make estimates of how they're going to behave in the real world. So you can train, sometimes you are able to train the users. And then specification of requirements. So you can figure out, okay, depending upon where the problems are having, maybe you say, okay, because I anticipate problems here, you need to make sure that you sort of fortify that part of your network, or maybe provide some safety provisions for that part of your network because you know there's going to be conflicts there or something. So you can, as an agency, you can come up with the requirements based on what you're seeing in the simulations. Like, you know, when you build a new system, you can specify what you might need. So these are sort of all different things why people use simulation, and that's in the transportation industry. But some things that to note here, the training is required. You have to be careful about how you use that simulation model. It's not always sort of this, you know, so there is a lot of information that goes into it. And then what you're going through in this class is sort of part of a training. And this class is not necessarily going to make you an expert in traffic simulation, but I think still could be a good starting point. Let me put it that way. So it's a good starting point towards learning of a simulation model. And I always think of like, whatever we do in the classroom, we talk about this learn by doing model that we have. And I don't like to think of this as sort of a class or any class really, and this class in particular also. It's not designed to be in a way that when you go into the real world now, you can basically build any kind of simulation. That's not what this class is going to be doing. I think that sometimes that's a mistake that we make thinking about these classes. What this class is designed to do is give you some learn by doing experience with simulation, so that whatever next problem that you encounter in the real world, you're prepared to handle that problem by sort of tinkering with it and learning on your own how to do that problem. So here you're going to see some preliminary problems. You're going to try to solve those problems by looking up this user manual, talking to me and talking to your colleagues here in the class. And then when you go out in the real world, you won't be ready to solve the problem that you see there, I don't think necessarily, but you will be ready with some experience in your head, because now you're prepared to learn how to learn by doing. So basically, we're not necessarily learning by doing as much as we are learning how to learn by doing. Right? Does that makes any sense, right? We're not going to see the specific problems that we work on in the class in the real world. There's no way that we can cover all the things that you're going to encounter in the real world, all the scenarios that you're going to encounter in the real world. This is just a practice to do what you're going to actually encounter in the real world. So not the specific thing, but generally speaking, the process that works. Because really what work is, when you go out in the industry, or what civil engineering practice is, it's all learned by doing. Right? You're going to have to do things, and you're going to learn to do things while you're doing those things. So that's what we are preparing you for. So not the specific things, but a practice of doing similar things that you want to do in the industry. So training, a lot of training is required, a lot of practice is required. And this is sort of just start of that practice. And then interpretation of results is not always obvious. So you have to think about, how to interpret the results. It could be time consuming and expensive. It's obviously it's going to be cheaper than tinkering with the real world, but it can still be time consuming and expensive to build that model, because a lot of good data is required. You require a lot of data to be able to build that model. And sometimes people will, because you see these fancy models, sometimes they're not appropriately designed. Sometimes they might have sort of this garbage in, garbage out type of quality, right? Where they're not putting in good data and their system is not behaving appropriately, but they're still able to generate some fancy sort of simulation models that look nice and all that. But the most important thing is how that model is built. So we don't want to use the simulation model inappropriately, because what we are most interested in is the performance measures that come out of the simulation. Okay, so that sort of is our most important thing. So we don't want to inappropriately use it, because most important thing is to get good data out of simulation and not generate those fancy visualization, the kind of things that you see. They're good for, like, sort of wowing an audience or whatever, but the ultimate purpose is to get those good performance measures that we need from the model. They could be travel time related, they could be traffic conflict related, and they could be congestion related, queues, whatnot, emissions. They could be a lot more. And those things are only going to be reliable if you're using the model appropriately. Application areas, and by the way, simulation is not something that we use in transportation, right? Simulation it's a widely used application area. So there are manufacturing and materials handling. So by the way, so one thing I should talk about here is the student who built that model. And this is, as I said, it's an old model, and I'm sort of embarrassed to admit how old that is, but it still works, and still works for demonstration purposes. So this was developed back in 2011, I'm thinking. And the student who developed it was not a civil engineering student, he was an industrial engineering student. And he ended up working with Intel. because they also use simulation in their manufacturing process. So they used how, like, what material is going to be used and how is that going to all move through the supply chain, all that. So simulation plays a big part in a lot of different things. And again, the things that you learn in the class here, you might not apply them exactly the same thing, but this is giving you an experience in sort of solving the problems that you have at home, right? So that's the major goal. So public and health system, so they're using simulation models to now maybe training the doctors to do how to do operations on people and things like that. In military, a lot of times they're using simulation as to how a system might behave when something happens, when an event happens. Natural resource management, that's a big thing on how, like, how to simulate a system of a jet stream, for example, how it's going to behave when water temperatures change and all that. So it's basically building those types of systems. Obviously, transportation, we're going to focus a lot on that. And then computer system performance, like how a system will behave, which is a computer. And those simulations, when human beings are not involved, those systems could be easier to develop sometimes. And then in communications as well, how you're gonna, how you might have at different locations, if there is, the quality of signal is not good, how do you sort of backfill that data and whatnot. So a lot of applications areas. I'm not even an expert in any one of those except a little bit in transportation, but everything else, but you can find like simulation, like a mathematical representation of the real world systems. That itself is something that we use in a lot of different fields. Okay, so I think that's about it. So about the presentation, I'm going to stop now and talk to you. Like, are there any questions about simulation as a whole, a transportation simulation, continuous versus discrete, micro versus macro? Micro is basically individual level interaction. Macro is like, treating the whole thing as one thing. And as your systems sort of get bigger and bigger, as your scale of your model goes bigger, it's going to become more and more difficult to do micro level analysis, right? So if your system is too big, then you probably stick with the more macro, or like they call it meso, sort of in between level analysis. We'll come to that when the time comes. But for now, are there any questions that you want to ask? So one thing that I want you to think about, and this is sort of your homework number one here, is that if you go back here, so I showed you that model, right? The simulation model for the Cal Poly campus. What I want you to do is think about what type of data do you think might be needed to create a model like this. Yes, please. It's not available. I know I'm going to have to change that. Thank you for reminding me. It says that it's going to be available after April 1st or whatever. But because I think that had something to do with, yeah, I'm going to make it available today, right now. And but you could see the problem on there. What type of data might be needed to create a model like this? Submit a bullet list of data items that you think might be. Okay, so let's think about this a little bit for 1 minute. And not all homeworks are going to be like this, where we're going to discuss the answer beforehand. But let's kind of maybe take a minute to think about the Cal Poly morning traffic simulation model that you saw. Is that like what type of data do you think went into it to build that model? Yes, Rob. Traffic counts at different locations, definitely part of it. You need those traffic counts to figure out how many vehicles are going to pass through. But it's a complicated issue, though. It's not real obvious, like, how to use traffic count when you're building the model. It's not real obvious, because when you're building the model, you can use traffic counts as, like, if you're modeling just one location, one intersection, then maybe having traffic counts is enough, is all you need. Because in a traffic intersection, if you have the turning movement counts, that's all you need. If you know how many people are going through, right and left in each approach, then you're good. But in a model like the one that you saw, traffic counts, let's say if you knew traffic counts at certain points on this Cal Poly map, right? So let me Let me pull up a little map of Cal Poly here. So I'm sharing screen. Yeah, so I think I'm still sharing the screen. So I don't know if I can. So this is our campus, right? So let's say you knew. So let's say you knew the turning movement count at this intersection. So let's say you knew the turning movement count at this intersection. What can you do with that information in terms of the bigger model? That's not going to be enough, right? You don't know, you don't just need it at one intersection, right? You probably need it at more locations, right? So let's say you knew the turning movement counts at this location, and then you knew the traffic count here, and I can zoom out a little bit here. I'm going to zoom out, and let's say you could clear the drawings. But let's say you could get traffic count here. You could get traffic counts from these exits and so forth on Foothill Boulevard. So you probably have some traffic counts here, and then maybe you have some over here on that road. Maybe you have some counts on the ramp, right? And then maybe you have some traffic counts at like on the different entry points for the campus, right? So I'm just trying to ask you to think about, like, if you knew certain counts at certain locations, how are they useful? I mean, obviously for the purposes of answering the question for this lab, traffic counts is a good answer. I will accept that. That's perfectly fine answer that yes, you need traffic counts. But let's say you have these traffic counts here. How does that help you build the model? Yes.
So you can sort of see the inflow and outflow of traffic in different areas.
Right.
You can sort of identify sort of congestion areas.
Right. You can identify those congestion areas, but that can help you validate the model if your model is doing a good job or not. But when you're building the model, you need to translate these traffic counts into what we call the OD flows, origin destination flows. Right? So what you really need is, when you're building the model for a large scale community like this, like a campus level model, now it's the same thing, right? Think about it at one intersection level. At one intersection, so if you have, like, let's say, I'm just going to draw out one intersection here. The one intersection, if you have turning movement counts on all of these, if you're modeling just one intersection, if you have turning movement counts at all locations, then you have the origin destination essentially. Right? You know what traffic is going from, what traffic is going through, what traffic is going from here to here, what traffic is going from here to here, and all those four approaches, right? So what am I missing? So yeah. So you have all four approaches like that. You have traffic counts, and then you have how much traffic going left and right. So you have what we call the origin destination flows. It's very easy to get that if you're just modeling one intersection. But if as you're modeling a larger and larger network, figuring out how much OD, origin destination flow there is, can get complicated. Right? And simply having the AADT, the average daily traffic, or even peak hour traffic volumes at locations that I was showing you earlier, at these marked locations, the locations like here, 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 they might not be enough by themselves. So what you need to do is, you probably need to convert these traffic counts into some sort of an origin destination flow to figure out, where these traffic are coming from and where they're going. So you need to kind of allocate that level of traffic. So what you need to think about is, what are my key origins for my network and what are my key destinations for my network? So if you're trying to do, and this is all context dependent, by the way, right? So why is it context dependent? Think about this. If you're talking about morning peak hour, your big origin would be maybe the freeway exit maybe where the people come into the campus from. So those would be your big origins, right? The big origins might be that intersection near sort of this Highland Drive intersection, maybe over here. So you need to know that, right? The traffic coming in from here, probably need some traffic coming in from here. So the peak hour traffic flow that's coming in, it's going to give you an idea about how much traffic is coming in from here. But you still don't know where they're going. So you probably need to do some, and my student had to do, is look at during the morning peak hour, which parking lots are getting filled up. So those become your destinations. So you need to get some sense of what is your OD flows. It's not an obvious problem, by the way. As your network size grows, this is not necessarily obvious. And although in a 10-week quarter, because you're just starting it out, we are not going to do a problem solve at this level. We're not going to solve this level of problem for OD flows. But we will do that for US 101 freeway and its on and off. And again, we'll again have the traffic counts at certain levels. And then we'll know the ramp counts a little bit. And then we'll make certain assumptions. We're going to build a model. And then we're going to check back. So what you do is you make an OD pair assumption. And then you model your system. And then you compare it to these traffic accounts that you have at these points and see if you're getting the right traffic. Is your model predicting the traffic that you see in the real world? Right? Based on the OD assumptions that you made, origin destination assumptions that you made, are those assumptions getting you the traffic count that are observed? If they do, then you have a validated model. If they don't, then you still need to tinker with your OD flow. Yes.
So is it possible that the traffic counts match with the time does it match? Like the speeds at which the cars flow in the simulation versus traffic?
So the question is, what if the counts match, but the time doesn't match, in the sense that what if the speeds are not matching, right? So that's another question, right? So so that's not good either. So you have to, so when we say validation, there's one more step before that is called calibration. And the idea of calibration is your system model after the real world system. So you want to match your speed profile first. So that's also part of, so because going back to the question that we'd asked, what type of data do you need? You also need that speed profile. So you're going to need the traffic count data that you're going to have to somehow convert into origin destination flows. And there are modern ways of doing that, by the way. So now we have sort of more technology. You know, in the olden days, sometimes we used to do these license plate surveys by looking at observing the license plate at the starting point, and then at different destinations, how many of the license plates you observed at here ended up at that location or ended up at XYZ locations. So we could split the traffic that way too. So there are other ways of doing that OD thing, but then one more important thing is it's just not about the traffic counts. You have to match the speed profile as well. And beyond that, you have to match what we call, sometimes, depending upon your application, like let's say if you're really interested in safety level analysis, you want to be able to estimate the conflicts, then you probably need to maybe video record the data at a certain location and see if you're even capturing the headways correctly. Individual headway distribution is matching the real world or not. So it's all sort of context specific. What other data? We got this, we talked about the speed, we talked about the traffic volume. What else? Yes, Tim.
I thought the roadway geometry would be important.
Yes.
So you could maybe do like geospatial data with the roadway.
Yes.
That would have like the number of lanes.
Yes.
The turning movements available. Sometimes like speed limits could be.
Yes.
Or
Yeah.
the traffic signal.
Yes, signals. Yeah. So basically all sort of geometric design data, right? So your roadway geometry, number of lanes, bike lanes if they are there, vehicular count, bicycle count, pedestrian counts at different locations. And then you said signal timing. Yes, absolutely, signal timing. You need that. Well, what else? Yeah, so I think those are all important things. Now, good thing is that when you use vSIM, they have sort of a background map available for you to use. So you can trace along that, and then you can zoom in and see So they have the maps, and then you could zoom in and see, you know, they even have satellite images available so that you could see how many lanes there are. You obviously have to be careful that the map data is not too old, or the real world doesn't look too different from what you have right now in the maps. But yeah, so all those things would be important. So I think that pretty much covers the data that you might need, and then some of that data might be useful for sort of modeling. What you call the modeling the network, and then some of that data would be useful also for validation of the network. Is it behaving the way it's supposed to behave? And it's very important for us to validate the existing conditions, because once we validate the existing conditions, then only we can make any inferences about future conditions. So that's basically the assumption, is that if we make a good model that replicates the conditions and the type of behavior of today, we can now start to maybe tinker around with things, like maybe convert a signalized intersection to a roundabout, or maybe move 5% of the traffic from cars to the buses or bicycles, and then see what time congestion might look like at different locations, things like that. You know, there might be some congestion we cannot do anything about, right? So for example, think about this, right? If let's say you make a Cal Poly campus, make the Cal Poly campus a bicycle friendly campus, and you switch 10% of those trips from cars to bicycles, but that wouldn't do anything to alleviate the traffic flow that's turning right from that 101 exit and making a right on California Boulevard. I think that will be this intersection. So if you kind of go back and look at this, I want to show. Even if you move cars to bicycles, I don't think this intersection would be impacted too much by that, because this is the traffic coming from North County, right? So they probably are not going to be switching. I think for them, the switching would be different. So if you say, like, I'm going to move 10% of the automobile traffic to bicycles, you can't just uniformly reduce your automobile flow by 10%. You have to be careful about where you make that demand adjustment. That adjustment would probably have to be made. Maybe folks that are coming from California over here, maybe coming from Foothill and those entrances, and then probably not. It's not going to make that much difference. Also, from the Grand Avenue entrance or exist also. So a lot more things to think about as you model a system like this. So yeah, make sure that you submit that assignment. I'll make sure that it's available to you. So that's sort of, you know, your first, or you could call it 0th homework, right? So just to start out. So a model like that. Thinking about what type of data. I don't know if there is anything else that we need to worry about, but think it through. Maybe there is some ideas that will come up. Okay. So I'm going to take a little pause here, maybe 5-minute pause, and then we'll talk about our first lab. You know, starting our 0th lab, right? So we'll talk about that after maybe